meaning that when you are attempting to minimize a regret, you may realize that there are solutions that give an unexpected outcome. But InfoGap is the only one that says, besides plotting a robustness function, let's plot an opportuneness function. Okay, robust optimization, it's very simple. We know what optimization is. We have to find the best parameter, and you may have what we did in optimization. It's to find, for instance, the max of sum of square. Epsilon is the error of the model, so we found this max. And what we did was to give a range for the parameter to be optimized. For instance, let's suppose that we want to estimate the k parameter of the linear reservoir. We said it has to stay into an interval that may be from 1 to 1 million. When we did in R optimization for I mode, we gave a range for the parameters. Okay, we didn't put any other constraint, meaning that this is not really a constraint. It's something that it's a range for the parameter that helps the program to find the optimum. But we didn't put any constraint. Usually, in optimization, we are also allowed to put constraints, which means that, for instance, we may want that there is a minimum flow that is left into the river when we design a water withdrawal. We made this example. And this minimum flow, it's environmental flow, it's a constraint. So if we looked for the optimum of a benefit function for the design of a water withdrawal, we would end up by taking all the water from the river. So we say no, we put a constraint, so I look for the optimum by keeping the constraint. This constraint may be uncertain, and this is when robust optimizations comes in. So we may say that k, for instance, should be greater than, in order to make reference to this example, k should be greater than 10. This is a constraint, which is different than saying look for k inside this interval. Or we may say k should be greater than 10 plus minus alpha. This is a constraint with uncertainty. So robust optimization means look for the optimum, but in the presence of constraints that are uncertain. This is very easy. It's difficult for me to make a practical example because this one is not really enlightening, because it makes confusion between the constraint and the parameter range. And I would need more time in order to provide you with an example. But in any case, just keep into account that robust means that your constraint to search for the optimum are not fixed. They may be varying. It's not widely used in our context of sustainability. Also, InfoGap, it's not widely used in the context of sustainability. Why it's not widely used? Because, you know, InfoGap and also this method, they rely on some quantification of uncertainty. InfoGap says what is the max range of uncertainty that I can tolerate. But then I need to compare this max range with my actual situation. So is my actual uncertainty lower within this range, max range tolerated or not? And then it comes into play some subjectivity. If you are lucky, you may have a probabilistic, as I said, assessment of uncertainty, but this is not often the case. So the consequence, the outcome is that InfoGap at a certain point asks you to make an assessment of uncertainty which may be subjective. And therefore, it's not really widely used. And the same for robust optimization. If I want to put uncertainty in the constraints, then what is the outcome from the discussion? If I am discussing with several stakeholders, I may say that rainfall is uncertain in 10%, but then people would ask me, why is that? Why do you say 10%? What is the basis? And either I have a rigorous approach for demonstrating that it's 10%, otherwise it's a problem in a discussion. Robust decision making is already a reply to this problem. So what is here the idea? Okay, the idea is let's try to agree to consider all the possible future scenarios. So are we talking about climate change? This method, as I said, we're developing in this context. It's difficult to agree with people what the future climate will be. So an idea could be, let's consider a wide range of scenarios. To reach an agreement by taking the opinion of everybody. Of course, there will be nobody that says that in the future rain will go to 0. There will be somebody saying rain is going to reduce 10%, other people 20%, other people 30%. Okay, let's take the widest range and generate a series of multiple futures. One may use, for doing that, one may use climate models, but not necessarily. Let's generate, as I said, a multiple set of possible future, not probable, possible. And I use the term possible, meaning that we are not necessarily using probability. We are not necessarily using a formal approach to do that. And let's generate, with some way, the future climate. Okay? So, it's written here. These multiple views of the future are created by just looking at their possibility without necessarily taking into account their probability. So even if they are unlikely, let's consider them. Okay? So, robustness with respect to those multiple views rather than optimality is adopted as a criterion to assess alternative policies. So, okay, let's suppose that we have this million of possibilities. What is the decision that is more robust with respect to this million of possibilities? Of course, you need a measure of robustness, which may be minimum benefit, which may be minimum regret quantified in some ways. You need to introduce an objective function. And let's look for the decision that, as I said, gives the highest robustness. And then, in evaluating these alternatives, you will have several scenarios. If I take decision A, maybe build a dam, what happens with respect to these multiple futures? If I decide, instead of building a dam, I decide to change the irrigation techniques, what happens with these multiple futures? And you will see that any decision is any different alternative is vulnerable with respect to some scenarios. And this will bring unexpected outcomes. Because when you discuss on an heuristic basis, it's very difficult to perceive what may happen in a wide range of scenarios. So, at the end of the story, you will have you may make an analysis of these vulnerabilities of each decision and what are the possible responses in terms of, okay, if this happens and this decision turns out to be vulnerable, what can I do in that case to recover? And this sets the basis for analyzing it directly with respect to several futures, what happens if you take a certain decision. And then you select the most robust. Of course, you may say, but this, you may say some limitations, like this wide range of possible futures may make the problem so complicated that it's difficult to resolve it, to find a good alternative. Actually, what happens usually when applying these methods is that there will be some future scenarios for which there is no solution. So if one say rainfall is going to decrease 80% in the future, you will see that it's something that whatever decision you take, you cannot recover from. And therefore, these scenarios may be rejected. On the one hand, because there would be no solution for that at the present time. On the other hand, they may be rejected because they turn out to be very unlikely. Because one thing is to say rainfall is going to decrease 50%. Another thing is to realize after a simulation that if this happens, it means that we need a profound change of our societal apparatus to be able to respond to this situation. And then people may realize that it's unlikely that it happens. And also you may bring some more information in, like, okay, let's look at the past. Rainfall didn't change or changed 1%. For what reason? In the next 50 years, are you predicting that? Are you predicting a situation that would change radically our environment, and you show it with simulations. So actually, this kind of testing with several alternatives and several scenarios gives the ground for informing the discussion. So this is the idea. Instead of looking for the max uncertainty that can be tolerated, let's look at the effect of uncertainty. The real effect and their implication. Okay, and let's see what are the steps, because this is an analytic method, it has steps. So in step 1, we have the identification of future scenarios. System models, meaning that you need to agree on the model to simulate these scenarios and a model to simulate the effect of your decision. Like if I build a dam, what kind of model do I use for predicting the benefit from the dam? And we need to agree on the metrics to evaluate success. So what is the metrics? Is the economic benefit? Is environmental protection? This is already a kind of discussion that is interesting. And pairwise comparison may allow you to give weights to several different metrics. Okay. And now we have we need metrics to describe how well future goals would be met. Okay. And furthermore, candidate strategies are to be discussed here. So what can we do? Build a dam, change irrigation techniques, whatever. Okay. This is step 1.
Excuse me.
Yeah.
You were speaking about the multiple views. I want to know multiple views of who? A group of experts, or everybody can participate in these views? Or?
No, we are talking here, we are talking here about multiple views of the future. Usually what it is meant here is multiple future climates. But you may generalize it in saying multiple scenarios of the future, which is something that can be provided by personal view or by a model. in these applications to water resources management, we usually mean multiple climates generated with climate models. On the other hand, I often argue, as we discussed, that climate models give only a partial view, and therefore other models should be used to predict multiple futures. On the other hand, sometimes I ask the stakeholders, like, okay, give me your view. So if you don't trust in my model, give me your view and I can consider it. And very often people say minus 20% of something. Okay? And as I mentioned to you. And so, for instance, now I am doing a consultancy activity for optimization of water supply systems here in Bologna, and they asked me to check what happens with the minus 20% water resources availability. And then I said, okay, that's fine. It's not coherent with what I am expecting personally, because I don't think in the future there will be minus 20%. I told them, but I said, fine, we can check it. And then we show, for instance, that, I'm not sure because we are making the computation, but one could show that, look, if you take minus 20%, there is no way to provide a response to this situation in the present time, because in the future there might be other opportunities, like desalination, for instance. But I could say there is no way, and therefore let's forget it, because let's wait. And it's better to wait what happens and to work for the minus 5 at the present stage. And, but in order to do that, I need to make a simulation. I need to show, according to this procedure, that their future is either unlikely or cannot be tolerated. And this is, anyway, a way to convince that if there is no solution for minus 20, you have to look for other targets. Because, I mean, what I usually say is, look at your present situation. You have some problems, or you have some concerns. If you have some problems, you have to resolve them. So a strategy, in any case, is to be elaborated. If you ask me to predict this strategy with a minus 20, I show you that there is no strategy for addressing a minus 20. This doesn't mean that you don't have to do anything. You still have some problems to solve. So let's plan for minus 5%, which allows you to find a solution to address your current problems. So please don't forget about them. And then, if in the future there will be an additional decrease of your availability of water resources, we will see what to do in 20 years from now, maybe. But what I usually regret about concern on climate change is that the predictions are so bad that people turn out not to do anything, and they don't solve the current problems. So the concern about a very bad future in 50 years from now brings us not to react to resolve current problems. This is the main issue with climate change. This is what I say, don't trust these predictions, because you have to trust on what's happening, because what's happening gives to you problems that you have to resolve now. And then, if in 20 years from now you will have additional problems, we will see, people will see in 20 years what they can do. But let's not to forget your problems now. Another example, very meaningful example, is that people are building their homes very close to the rivers where it's not allowed. And then what happens is that they get flooded, okay? And then we look for solutions. And there are several possible solutions, like building a levee, building a dam upstream. You get together to decide, and then if you take climate change into play, there is no solution. And people often say, okay, let's minimize CO2 emissions, let's make a call to the politicians for minimizing CO2 emissions, and they don't solve the current problem. The current problem is that this person should be moved from the floodplain to another place. But usually, given that this move is problematic, because people don't want to move, they want that you build a levee, you do something else, but Again, if you take climate projections, it's no solution. You cannot find a solution. So the result is that we don't do anything, and people continue to die. So, I mean, it's extremely important that we are very empirical in this case. So let's focus on the current problems, and then if you have some ideas about future possibilities, let's see what happens. Let's test the decision, no problem. Okay, now, as I said, multiple views of the future, alternatives and metrics, and then we can evaluate the system performances in a step 2, and which means that you see what is the effect of your decision with respect to these multiple views, as I said. And it is termed experimental design. And so we evaluate the performances of alternative strategies with the related metrics. And then in step 3, we assess vulnerability. So we point out what are the weaknesses of each alternative. And then we try to identify that what are the strategies that minimize vulnerability. And there is an additional step that you may undertake, which is to try to profit from vulnerability assessment to refine your decision. So we identify the alternatives at the beginning, but by assessing vulnerabilities of these alternatives, you may also seek to improve them. And I have a sketch illustrating robust decision making, and let me first finish with the steps. And okay, this is what I already mentioned. So adaptation option, which means adapting the strategies, and risk management, which means that at this stage you could bring into play the likelihood of the future scenarios. So at the beginning, you just take everything. Everything is possible. At the end of the story, as I said, we may say to people, look, this scenario that I considered because you asked me to consider it is highly unlikely. So let's forget it. And this is a final step of the assessment. As I said, there is a sketch that is very useful, which is this one, and here is the RDM, robust decision making. So you start with candidate strategies, you evaluate the strategies against the scenarios, and then you estimate vulnerability, and then you may elaborate and test new strategies. If you take this final step, you can go back to evaluate strategies against scenarios. This is, by comparison, what is usually done so far. In 99% of the cases of climate change impact assessment, what people do is to generate future scenarios with climate models, get design variables, which very often imply the availability of huge resources to find a solution, and then at the end of the story they try to see what is the vulnerability of the system and the strategies according to each identified solution. So basically, they usually consider the scenarios at the beginning. In this case, you see that we start from the strategies, so we don't start with the scenario, we start with the strategies, and then we evaluate the strategies against the future. It's a different approach. And okay, now there is another approach, which is decision scaling, which is similar to robust decision making, but with some differences that I want to point out. Okay, what is decision scaling? It's another analysis that doesn't start with climate projections, but starts with analysis of vulnerabilities. So it doesn't start with the strategies like robust decision making, but starts with an analysis of the vulnerability of the system. And the term decision scaling, it refers to downscaling of climate information, because this method was developed within the context of climate change. And so it's I don't think it's a name that really reflects the behavior of this method. I just wanted to tell you that scaling refers to downscaling of climate information, but I don't think, I think it can be understood if the method is applied in the context of climate change, but I don't think this name is really reflecting, as I said, what the method does. And basically, the difference is that the climate information is used in the last stage. We will see how it works. And basically, it starts from a model of the system and determines through a stress test what are the conditions that bring the system to fail. This is the concept. So, robust decision making starts from the decision and then alternatives, and then brings climate information in and studies the vulnerabilities. Decision scaling starts with the analysis of the vulnerabilities of the systems. So what are the conditions that bring the system to fail? Any alternative to fail? So in the first step, the vulnerabilities are identified, and they can be defined in terms of the external factors and the thresholds at which they become problematic, a situation becomes problematic. So we may say, for instance, that our current system suffers from a reduction of water resources availability, and it starts suffering at a level of minus 15%, for instance, suffering in a problematic way. So we analyze thresholds, vulnerability, and then in the second step, future projection of climate and other information are used to characterize the relative likelihood of this condition occurring. What is important here, so climate information is used only after vulnerabilities have been identified. What is a distinguishing feature here is the fact that this method explicitly admits for additional information besides climate projections. And this is the first method that I see admitting that climate projections alone may not be enough. And in the paper that proposed decision scaling, the authors specifically mentioned stochastic simulation, which means get any information that you may have on the future and test whether these futures can make the system vulnerable. Okay, and then you plan the strategies in order to minimize these vulnerabilities. And the result is a vulnerability domain according to this sketch here. Assess vulnerabilities, future scenarios, further information, which may be stochastic analysis, elaborate strategies to minimize the risks to system. This is a different approach. If you concentrate, and of course, they are very similar. I mean, the differences are subtle and are to be looked in details, in conceptual details. So here I start with the strategies and then I evaluate the effect of these strategies. Here I first start with vulnerabilities. I look at the scenarios to see what are the scenarios that make the system vulnerable, and then additional information and then elaboration of strategies. The process is very similar. In fact, there are studies that compare these methods. There are studies comparing InfoGap robust decision making and decision scaling. And they find usually that under some conditions they go to the same, they converge to the same solution. But especially if the solutions are in a limited number and they're relatively easy to identify. In some cases, they provide different insights that may lead to different decisions. Again, there are softwares for applying these methods. Okay, now I would like to make a mention to multi-criteria decision analysis and pairwise comparison, analytical hierarchy process, because you may wonder at this stage what is the relationship of the methods I mentioned today, basically InfoGap, robust decision making, decision scaling, robust optimization, with the analytical hierarchy process and pairwise comparison. Indeed, there is a relationship, meaning that the example that I showed you about pairwise comparison 1 week ago, pairwise comparison can be adapted and used to be a robust method, or pairwise comparison may be included into the methods that we discussed today. Let me try to be clearer by first talking about multi-criteria decision analysis. What is multi-criteria? It's very simple. Sometimes you may have not just one objective function, but more than one. And this may happen in an optimization problem, but it may happen also in the robust methods that I discussed today. Because these methods, InfoGap, robust decision making, decision scaling, any of them at a certain stage contains an evaluation of the effectiveness of strategies. And as I mentioned, you need a measure of success. This measure of success typically is your objective function, but it could be more than one objective function. And then you fall back in the multi-criteria case. In the multi-criteria case, as I said, you have more than one target. So, what could be the solution? The solution could be the easiest one, the most, not the easiest, but the most natural one is to look to combine these targets, this objective function, into one aggregated score. In order to do that, you need to make a weighted average of the individual objective functions. And to be able to do this, you need first to express the objective functions in the same range, so you have to rescale them. This is what we mean when we say we need to rescale the targets. Usually the range is 0, 1. You remember the exercise, we rescaled through the utility function in the range 0, 1, the various objective functions. And you need to determine the weights of each objective. We know how to do that through pairwise comparison. This is the first solution. We are still in an optimal context here. In fact, the exercise that we did, we were still in an optimal context. Okay. There are, I want to mention them, other methods for dealing with multi-criteria decisions. There is a method that is frequently nominated in the literature, which is, I just want to mention it. it doesn't identify a combination of objectives, but identifies non-dominated solutions. What is a non-dominated solution? There are several candidate solutions. A non-dominated one is a solution such that another solution doesn't lead to an increase of all the objectives. I say again, if a solution is non-dominated, it means that another solution doesn't lead to an improvement of all the objectives. Another solution may bring to an improvement of one objective, which is compensated by a disimprovement, a decrease of another objective. Because of course, if a solution is dominated, we reject it. What's the reason why I should consider a dominated solution? I take the other one, which gives better performances in all the objectives. So, you restrict the domain of the solution to the non-dominated ones, and then you remain with the problem of selecting one of the non-dominated solutions. But the problem becomes simpler. And there is no response to the identification of the best solution among the non-dominated. It depends on the user. These are also called Pareto Solutions. I just want to mention the terminology without going into the details. And there are plenty of methods for identifying, given the objective functions, more than one, the non-dominated solutions.